radius now we have 55.
Yeah, nobody else wants to do makeup, so I can do T55. Draw us a nice little photo too.
Yeah.
Oh, you even get to bump us up into the measurement section.
I can't believe how many of these we've mashed through.
Yeah, I feel like in the beginning it seemed like we were going through them so fast, and now that they've gotten a little bit harder and a little bit longer, the pace is kind of slowing down a little.
Well, I'm hoping some of the measurement ones, once we figure out how to do them, will speed up.
You think those are a little easier or more succinct?
Some of them are. Till we get to the ones I marked L's on down there.
Yeah, I actually took one that was an L.
All right.
I think most of them were already
I got
in one.
the sum of the measures of any two angles in a triangle is less than 180. So it's like, let ABC exist. Nice little triangle. Now let D be a point on, let's label this so this makes sense. On AC such that you got A star C star D, so somewhere over here. Also let F be a point on AC such you get the opposite. So that's over here. So now I have a triangle point from it. Then angle BCD and BCA are supplements by D15. And also BCD is the external angle of the triangle by D25. Then by T53E, that is the measurement of supplement angles equals 180 degrees. So these bad boys add up to 180. And then by T46, we know that the angle BCD is greater than the angle ABC, and that is the external angle is greater than any of the opposite interior angles. And then by T53F, I can't remember that one, but I do know the measurement of the angle BCD is greater than the measurement of the angle ABC. That lets you translate if, essentially we're now saying if this angle is bigger than this angle, it measures bigger than that angle. That's what lets us translate between the two. So then you get this little nice inequality here. The measurement of the angle ABC plus BCA is less than measurement of BCD plus BCA, and that's because we know that BCD is greater than ABC, so therefore when you add them together it has to be less than. So we know that's less than 180. And then you do the same for the CAB.
Which is the other remote interior.
Which is the other remote interior.
Okay.
And that's why you have to, because you can only get the two remote interiors and you need any two. So that's why I introduced the F over here. So then, again, FAB and BAC are supplements by the same stuff, and then they add up to 180 by the same stuff. And then by T46, T25, same stuff, same reasons about why they're bigger.
You just had to switch exterior angles to get the one that you're now targeting to be a remote interior.
So then we show that the measurement of the angle ABC plus measurement of the angle CAB is less than the measurement angle FAB plus measurement angle BAC, which equals 180. So therefore, the sum of any two angles of a triangle is less than 180 degrees. Any questions? I spent 2 hours thinking about this one before I actually had my list in front of me. And I would suggest anybody that's doing measurement lists, measurement proofs, at least the first couple ones, you can use the stuff before the measurement section. Because I was lost just looking at what was given in the measurement section. How am I supposed to do this?
We've got to move it forward.
So I don't know what the little circle is called that indicates degrees, but you used it like half the time.
Half the time I was lazy.
Yeah.
But yeah, that's a little typo that I can easily fix.
Can I ask you this? Was it nice working with an actual number?
It's almost like a place marker in this math, though. It's like it's just less than this place marker 180.
Yeah,
it's nice to type it, but I don't do anything with it.
There's no calculator.
Yeah. There are a few later where you do get to do some calculations with it.
Yeah. Some of this feels real ethereal, like it's just out in the ether somewhere. it feels very vague, it's hard to grab, it's like.
And if you say this out loud to people, they're like, duh.
Well, and the one though on the triangle is weirder because it's going to say that the angle sum of the triangle is less than or equal to 180. And as soon as we get the hyperbolic axiom, we'll prove it's actually less than 180.
Wow.
So in Euclidean geometry, the angles of a triangle always add to exactly 180. In hyperbolic geometry, they always add to less than 180.
Dang, that seems really confusing.
So the world just becomes different.
It goes against everything we were taught in high school geometry. Because in high school geometry, we were taught that the angle sum of a triangle is always 180.
So when you are doing these, you do want to think about the measurement facts. So you'll notice that in 52 and 53, they kind of give you what you would expect. That your measurement should be positive numbers. Nothing's going to measure 0. That measurements are equal if and only if segments are congruent. That if segments are smaller than each other, their measures ought to be smaller than each other. If you can add segments to make a longer segment, you should be able to add their measures to make the longer measure. So that's exactly what D is telling you. By knowing C star D star E, you've got a segment CD and a segment DE that should add up by the old add segment thing for congruence, but now it adds numerically. Angles, it's a little bit further because it says we're going to restrict angle measures to be strictly between 0 and 180. So that's what's saying we're not going to measure a straight angle. And we talked about during the review how a straight angle isn't an angle by our definition. And so that's why it stays less than 180. But right angles should measure 90 degrees. They always have. They still should. Equal measures, congruent angles. And then you've got the same thing. If you set it up so you could add angles, you ought to be able to add their measures. And we've got supplements adding to 180 and then the inequality piece holding. We've got quite a bit of time left. I can give you a little bit of an idea of how they prove this, but we do not want to have to prove it.
So that's why it wasn't on the list.
Yeah, but let's think about it a little bit since we've got some time.
One thought I had is, it seems weird to me that the definitions of measure of the segment and angle are after T52 and 53. Like, it seems like they should come before.
Yeah, probably. I think part of it is, though, those two theorems are what are telling you that those definitions are well defined. Because I do not know what the measure means until I have theorem 52 and 53. I don't know that that symbol gives me a unique value. So frequently you'll have a theorem that kind of proves what you're trying to measure is well defined. Or what you're trying to define actually exists. And can be defined uniquely and all of those types of pieces. So in lists, you'll often find there's a theorem, and then there's the definition where you name what you're getting out of that theorem. Lots of theorems cheat. And they sort of say, here's the theorem about this, and we're going to call it measurement. And they just put it in the theorem statement.
They don't give you a definition.
They don't list it as a separate definition. They just hide the definition in the theorem.
Okay.
And I can't remember if I did that any place in this list or not.
Well, it makes me think of that problem on our midterm where it's like, it would be weird to put them into the list like between, I think it was like 24 and 34 or something.
Mhm.
You know, if you didn't already know what the I can't remember what the context of that problem, but if you didn't know something before that about like coterminal arrays or the other piece, then it would be weird to like even have that theorem. Like you wouldn't know what you're doing. Like what does that even mean?
Yeah, so one of the problems is the coterminal arrays aren't defined in our list.
Yeah, okay.
And I think they need to be tucked in when we talk about the definition of an angle.
That was the equilateral, equal angular.
Yeah, that was what it was. And so if you don't have those definitions there, yeah, I can see why you need to put those theorems first, so you can get an understanding of what you're even doing. But, I don't know. I think it's just the notation is scary, and like when you see mu thrown in there, then I'm like, I want it like defined before I go into it. Kind of.
So mu is m.
It's just a measure.
It's just saying measure as opposed to segment. So you could say that what 52 does is define a function. And if we really wanted to think of this, we could think of mu being used as a function that goes from the set of all segments A, B, such that, oops, they're not use A and B though, those are a specific segment. All segments X, Y, where X and Y are points.
I'm sorry, are we still recording that one?
Yeah, I am.
Okay, cool.
Do you want me to not record?
No, I just want to make sure I can refer to this later.
That's why I put up the screen so I could go this way and hopefully it would be on the screen.
Yeah.
But you could say it's a function here that is mapping to C plus. And what 52 does is define the function for segments. But then we have this problem because we also use mu as a function for angles x, y, z, such that x, y, and x, z are rays. And then we map that to the open interval 0, 180.
Wow.
But you could think of them as functions.
Wow, this is reminding me of abstract algebra when we had functions like this.
Why is it Z plus for the segment? Why would it be?
Because the only restriction I think I have in that is that they have to be positive. Oh, and I bet it should be
Yeah.
R.
It's a
Yeah, that's what I was
positive real
thinking.
number, yeah.
Probably
You
should
got
be
to
R.
five, right?
And so if you go to prove this, you've got to set it up. And the way to set it up, you've got to pick what's going to be your reference length. And so that's where they say, we're just going to pick some segment to be 1. And then if I wanted to measure, so here's my AB, and let's say I wanted to measure some segment CD. What I could do is use axiom 9 to start building. Well, let's see, I can put a D1 here, and I get those two congruent. And then I could put a D2 here, and I get that one congruent. And then I can put a D3 here, and I get that one congruent. But then I have this little fraction left over. And so then I've got to decide, how do I define that fraction? And what you actually can do is start bisecting this, because we have a midpoint theorem. So I can get a length of a half, and a quarter, and an eighth, and on. And the Archimedean axiom says that, I can get to any real number by looking at a sequence of halves, essentially doing a base 2 function instead of in terms of fractions. And so what you would then do is start lining up fractions that would nudge out to this point. And the Archimedean axiom would be what would tell you you could fill that up.
Wow.
But then you've got to go through and make sure all of the other things are working. And it is tedious and it is long, and I haven't seen any book bother to write it down. But you can sort of see then you would do the same thing with angles.
Oh, using
Because you can say, well, I'm going to assume a right angle here. Your reference point becomes a right angle, which is your 90 degrees. And then you can start bisecting it as you shrink down to smaller and smaller angles. And then you could increase it by adding pieces up. And if you want the sums, we know that a straight line is built from 2 90-degree angles, and so that's setting you up for your straight line coming out of 180. But what the Archimedean axiom does is it essentially gives you limits. And in fact, I noticed that when Dusty was doing this, he added the analysis version of this, which says if you have any distance, you can find some natural number multiplier that you can multiply the smaller number by to get bigger than the larger one. And in both of those, what it ultimately gives you is a way to do limit approaches to things. So you can keep making them smaller, making them larger. But I did not decide to fill in those, just like all the books I've read decided not to fill in those, mostly because we don't have time. And so what I started with was triangle inequality, which somebody is already working on. Emma?
Yes.
And then we've got the one we just proved. So two angles will always sum to less than 180. 56 is really a lemma. What it's saying is if you've got a triangle, you can always get a triangle with a smaller angle by half.
So yeah, I think I selected that one,
Less than or equal to.
I
So if
might,
I've got a triangle like this, somehow I can get a new triangle with an angle that is smaller. And I want it to be less than half.
so,
You don't want it to be exactly that?
I think exactly half might be really hard. But it says I want the measure to be half or less.
okay.
One angle is
And which angle am I looking at? An ABC? Yeah. So let's say here's my ABC, and I got this big angle, and I want to try to build something that will be half the size.
Yeah, it seems like you could draw a picture quite easily.
Yeah, maybe play with midpoints or something to build new triangles. But you've got to work your way down to saying that this angle then is half the size.
Well, you can't use the angle bisector to just cut right through that?
I could use the angle bisector.
And then you would play with what? A, B, and X, and X, B, C?
Yeah, we've got to keep the same angle sum. So we've got to try to have a way to get the same angle sum. But if we did an angle bisector, then we'd have these two angles the same. This is still here. This is still here. We could see if we could get this angle to have the same angle sum. And we can do a lot with adding parts of angles in here. But I think there was a glitch with getting it coming out exactly 1/2.
Whenever you add two angles, you can only guarantee that's less than 180. Somebody has to play with that where you can't get it exactly 1/2.
Yeah, I don't remember what the glitch was. I know I went at it with midpoints instead of bisectors, but I'm not sure why that would make that much difference. But what it will allow us to do is essentially, if you have a triangle, and I knew that the angle sum was more than 180, I can look at how much more. And I can essentially build a new triangle that maybe has a really tiny sliver. Maybe it creeps out here, I don't know. But I can make it so that this one angle ends up being smaller than the overage. And then that follows up the theorem that the two have to add up to 180, or add up to less than 180. And so this is really a step in order to be able to iterate, so that I can shrink an angle and get a new triangle with a teeny, teeny, tiny angle, but the same angle sum.
So, but you're not trying to build two separate triangles, you're trying to dissect that triangle.
This says
down
two
further.
separate triangles, but one inside of another is separate too. I just don't.
Yeah, that's what I mean, like,
So it could be either way.
okay.
But it really is all to prove Sakari-Legendre, which is 57. And 57 is actually much easier than that the half exists. Because it's just going to say, by the Archimedean algorithm, I can do the halves and halves, and I can find an n so that n times this number is small enough, and happy. And then you can prove that the measure of an exterior is greater than or equal to the sum of the measures of the interior. So right now we know that the exterior is bigger than either interior, but we actually want to show that it's bigger than the sum of the two interiors. We just couldn't sum angles that weren't with a common vertex before. So that's where having measurement. And then 59 is really short. So whoever picked 59 scored a truly short one. Should be a double S. But you just want to show that a triangle has to have two acute angles.
Yeah, you can see that's super easy using 57.
Mm-hmm. Mm-hmm. And then we get to quadrilaterals. So the trick into finding a quadrilateral is sticky, though, because we just don't want to say find 4 segments, because I could do something bizarre like there are 4 segments that I can union together,
Yeah.
but that won't quite make a quadrilateral.
That's it, none of them intersect. Well, at the end, unless at the end points.
So you have to find some way to get rid of this problem, and I think I chose it by forcing things to be on sides. Is that what I did?
No, 3 of which are.
No, I did it so the segments can't intersect. So you could say that given any side, the other 2 points have to be on the same side. That would be another way to do it. But this one is done by just saying that the segments that form the quadrilateral can't intersect. So it gets rid of that twist piece. And then I did put in a few extra words in here along the lines of the test where I wish we had had more words for triangles. I threw in some more words for quadrilaterals. And do you know about convex and concave quadrilaterals? So that is not a quadrilateral. But I can have quadrilaterals that are interesting. I could do something like that, where it's like one corner's poked inside, or you can do something like this, where all the corners are poked outside. The ones where you can get an indentation and a corner. So essentially here I can think of a segment where I can connect 2 of the vertices and not have them cross that segment. But in here, that can't happen, because any segment that you do that connects opposite vertices is trapped inside the quadrilateral rather than slipping outside. These are called convex. This is called concave.
I think it's easier when I would just buy the cave in it.
Yeah, think of it as having a little cave. I think that's a great way to kind of remember it.
Yeah.
It's got a portion that's kind of caved in.
Yeah.
And so you're going to get a slew of definitions, which is happening at the beginning of each of these sections. But there's quadrilaterals, vertices, sides. Adjacent vertices and opposite sides are handy concepts. So adjacent vertices share are endpoints of a common edge. And opposite sides are ones where you use all 4 vertices. So 2 for one, 2 for the other. Rectangle, 4 right angles. Turns out in hyperbolic, rectangles don't exist. Another little oddity. All quadrilaterals have angle sum under 360. Goes with the triangles having angle sum under 180. We're headed towards weirdness in the future.
Yeah.
And then angle sum is just the sum of the measures. And so we'll talk about angle sum of a quadrilateral and angle sum of a triangle, except I don't know that I defined angle sum of a triangle.
You did, pretty sure.
Did I do it?
Some measure of angles of triangle ABC is called angle sum of
Oh,
triangle. So now
good. So I wasn't bad.
ABC.
But then we'll just play through some facts about rectangles. And it's going to take us until we get to about the last dozen proofs before we hit hyperbolic. But we're sort of setting ourselves up for that.
Yeah.
And we do need to kind of keep pace, because without starting measurement today, I have us averaging about 4 to 5 proofs a day.
So where should we get to by Wednesday?
So Wednesday, my hope was that we would get through 59. So probably anybody with 60 or less be thinking about Wednesday. And
Yeah.
so there's kind of an outline. You'll notice when I did my guesses on what we cover each day, I kind of had a backup a proof or 2 on the next day just in case. But we need to stay pretty well on schedule so that we can actually finish hyperbolic.
Yeah.
And we have 2 options for the final. One is to do it Monday 1 to 3, which is what goes with our 1:30 time. The other option we'd have is to do it Wednesday 3:30 to 5:30, which goes with our 2:30 class time, because we essentially fill 2 blocks on a Monday, Wednesday, Friday. I put on the syllabus to aim for Monday, but if we get too far behind in the hyperbolic and have to cram too much of that into Friday, you might want a review session at the beginning of the week and a little bit more breather. So I'll kind of roll with what you want.
I have, on Wednesdays, I have to work at 4:30, but I also take my test in the testing center, so I can try to schedule that whenever I.
Yeah, so we could juggle some of the time, but
Yeah, I can just.
I did leave that as an option just in case we needed it. And that's why it's on this tentative schedule. I'm kind of hopeful, though, that we can
Do it by Monday.
keep on schedule well enough. We'll see how it goes. But I'm afraid